title of the experiment is Linear Motion. There are two objectives. The first one is to investigate the relationship between forces, mass, and acceleration, and the second one is to determine the acceleration of an object under a varying force.
For theory of linear motion, the acceleration of an object is directly proportional to the net force acting on it, and is inversely proportional to the object's mass. The direction of the acceleration is in the direction of the net force acting on the object. As you can see, the formula is F equal to ma. Consider a mass m1 placed on a smooth table and is tied to a string that is connected to another mass which is m2 as shown in figure 4.1. As indicated by figure 4.1, when m1 is released, both objects will accelerate. The two masses will have acceleration which is a of the same magnitude because they are connected as a single system by n on a stretchable massless string. An analysis of the motion of the system, assuming that Newton's law of motion are correct, is set out below.
First step, the linear air-track set is assembled as shown in figure 4.3. Number 2, the pump is switched on and air is allowed to blow through the track for several minutes. The track is balanced by adjusting the screw on its leg so that the glider is kept stationary and does not glide to either end when released. Number 3, one hook is inserted at one end and the flag is placed on top of the glider. Number 4, the mass of the hanger and the mass of the glider are measured and recorded. Then, the length of the flag is measured. 5. One end of the string is attached to the hanger and the other end is tied to the glider. 6. A mass of 20 grams is placed on the hanger and 80 grams is placed on the glider. The string is placed over the pulley. Number 7. The glider is positioned exactly before the photogate. The glider is released and the time shown on the photogate is recorded. Note, to avoid the masses from crashing to the floor and scattering, the glider is coached mid-second before the hanger reaches the floor. Number 8. The procedure is repeated 2 more times to obtain average time values. Number 9. Then, the slotted mass on the glider is decreased by transferring a 20 gram mass onto the hanger. Step 7 and 8 are repeated. Number 10. The procedure is repeated 3 more times with 20 gram of the slotted mass from the glider being added to the hanger each time.
As for the data analysis, there are 8 questions. The first one is to plot a graph of weight, force F Newton versus acceleration A meters per second square.
This is the graph for question 1.
Question number 2. What does the graph tell us?
The graph plots force on the y-axis versus acceleration on the x-axis. The straight line passing through the origin shows a directly proportional relationship between force and acceleration. This confirms Newton's second law, where the slope of the graph represents the mass of the system.
Question number 3. Determine the gradient m of the graph.
The answer is 0.133 kilogram.
Question number 4. Calculate the uncertainties of gradient m.
The answer is 0.005 kilogram.
Question number 5. Briefly explain the relationship between the gradient m from the graph and the total mass mt equal to mt1 plus mt2.
From theory, F equal mt times A. So gradient equal total mass of the system, which includes mass of glider
and mass of hanging weights. Question number 6. Calculate the percentage difference between the gradient M and MT. What is the percent error in this experimental value?
The answer of percentage error is 5.0%.
Question number 7. Discuss the factors that have contributed to the error in the experiment.
Friction in pulley or track, air resistance or uneven airflow, slack or stretch in the string.
Question number 8. Explain how to overcome the factor mentioned in true wrong.
Use low friction pulleys and clean the air track. Use inextensible string. Repeat trials and average the results.
For discussion, in this experiment, we studied how force affects the motion of an object on a linear air track. The results show that as the force increases, the acceleration also increases, which agrees with Newton's second law. The graph of force versus acceleration gave a straight line, proving that acceleration is directly proportional to the force applied. However, there may have been some small errors, such as friction on the track, incorrect timing from the photo gate, or the track not being completely level. This could cause slight difference in the data. To reduce these errors, we should make sure the air track is balanced properly, use accurate timing tools, and release the glider without touching it too much.
Conclusion. The experiment showed that as the mass of the hanger increased, the acceleration of the glider also increased. This direct relationship between force and acceleration supports the concept of linear motion and aligns with Newton's second law, which states the greater force results in greater acceleration when mass is constant.
Today, we are presenting about Experiment 5, which is Hooke's law. The objective of this experiment is to verify the accuracy of Hooke's law.
The theory of this experiment is that the motion of a body that oscillates back and forth is defined as simple harmonic motion if there exists a restoring force F that is opposite and directly proportional to the distance x that the body is displaced from its equilibrium position. This relationship between the restoring force F and the displacement x may be written as F equal minus kx, where k is a constant of proportionality. The minus sign indicates that the force is oppositely directed to the displacement and is always towards the equilibrium position.
Procedure 1. The mass of the hanger was measured using a balance and recorded as M hanger. 2. The weight of the hanger was calculated using W equal mg and the value was recorded in the data table. 3. The scale was adjusted so that the pointer on the hanger was near the upper end of the scale when unloaded. This position was recorded as x0. 4. A 10-gram mass was added to the hanger and the corresponding scale reading x1 was recorded. The load was then increased by equal increments until 8 data points were obtained. Each total weight and corresponding position was recorded. 5. The process was then reversed by unloading the same weights. For each step of unloading, the new scale reading x1 was recorded. 6. The extension of the spring was calculated by subtracting the initial position x0 from each x1 value. 7. The force acting on the spring for each load was determined using F equal mg, where m is the total mass at each step and g is the acceleration due to gravity.
As you can see, this is our results for this experiment.
As for the data analysis, there are 5 questions. The first one is to plot a graph of the force causing the extension F against the extension X. Calculate gradient of the graph. What value does the graph represent? As you guys can see, here is the graph, and the gradient is 36.67 Newton per meter. The gradient represents K. Number 2. How much work done in stretching the spring through 0.20 meter? Find this from the graph. The answer is 0.11 joule. Number 3. How much energy is stored in the spring when it is extended to 0.20 meter? The answer is 0.11 joule. Number 4. Describe any errors that may have occurred during this experiment. The errors could be due to human error, such as incorrect reading of the ruler, and it could be due to measurement error, for example, inaccurate measurement. Number 5. What can you describe from your result about the relationship between extension of a spring and the force causing extension? Force is directly proportional to the extension of the spring.
For discussion, this experiment was done to verify Hooke's law by measuring how a spring stretches when different weights are added. The result showed that the spring extension increased in a regular way as more force was applied. The graph of force against extension was a straight line, which confirms Hooke's law. Some small errors may have affected the accuracy, such as reading the scale incorrectly, using an old or stretched spring, or unloading the weight too quickly. To improve the experiment, we can use the newer spring, read the scales carefully, and add or remove weight slowly and steadily.
Conclusion. The experiment showed that the spring stretched more as we added more weight, and the stretch increased in a regular way. This means Hooke's law is correct, as the extension was proportional to the force applied.